Hello, everybody. All right, welcome back. Um, Continuing Unit 1, Journey's Squeeze Theorem. Okay, so first, first I want to state the Squeeze Theorem, and then we're just going to go through some examples. I think that'd probably be the best bet. So here's the Squeeze Theorem. Suppose that f is less than or equal to g, less than or equal to h. Okay, so in other words, h is the biggest function and f is the smallest. Let's see. For all x near x equals a, yeah, near x equals a, then if the limit as x approaches a of f is equal to the limit as x approaches a of h, then the limit as x approaches a of g must equal the other two, right? Must equal the limit as x approaches a f, which has to equal the limit as x approaches a h. Okay, so what this is saying is that if f is the small function and h is the large function, and f and h have the same limits, since g is in the middle, since g is squeezed between f and h, that g must have the same limit. Okay, and this is particularly useful for bounded functions. Okay, functions that have a known max or min. So functions like sine, cosine, these are bounded. Let's see. Those are the only ones I can think of offhand. But you can create some situation. If you consider like any closed interval, as long as your function is continuous, then it's bounded as well. But it's particularly useful for bounded functions. So okay, let's go through a couple of examples. I think that will help us understand the Squeeze theorem. Okay. Here we go. This is a problem out of textbook here. It says use the Squeeze theorem to show this. Limit as x approaches 0 of x squared cosine 20 pi x equals 0. Okay. Use the Squeeze theorem. Okay. Well, first, here's where the bounded part comes in. So this x squared is not bounded, but cosine is. Okay, so the maximum value of the cosine of 20 pi x, maximum value is 1, and likewise the minimum value of cosine 20 pi x is negative 1. Okay, cosine is a bounded function. It's bound between negative 1 and 1. So what that means is that our function x squared cosine 20 pi x, our function is less than or equal to x squared times the maximum here, which is 1. And it's also going to be less than the minimum here. So what I'm doing here is I'm taking this minimum value and I'm just replacing it here. So x squared times -1, that's negative x squared. And x squared times the maximum of cosine, the maximum of cosine is 1. X squared times 1 is positive x squared. Okay? So we have this situation where our function is squeezed in the middle between negative x squared and x squared for all x. Okay? Now, this is useful because we know the following. We know that the limit as x approaches 0 of the function x squared. Now check this out. X squared is the limit of a continuous function. Limit of a continuous function. Since we know x squared is continuous, that means literally that the left-hand limit equals the right-hand limit, which equals f at a. Okay? That's what it means to take a limit of a continuous function. So if you have a continuous function, you can literally find its value just by plugging a into the function. In our case, a is 0. So the limit is just going to be 0 squared, which is 0. Okay? And likewise, the limit as x approaches 0 of the minimum function, negative x squared, this guy, is going to be the negative of 0 squared, which is the negative of 0, which is 0. Okay? So what that means is that our minimum here is 0. Our maximum here is 0. So we have this situation. Oh, I'm sorry. Let me write this correctly. So we have shown, because the minimum limit is 0 and the maximum limit is 0, that our limit in the middle is stuck between 0 and 0. So if the limit is stuck between 0 and 0, our only conclusion then is that the limit as x approaches 0 of x squared cosine 20 pi x has to be 0 by the Squeeze theorem. Okay, so we laid out the entire Squeeze theorem little proof there for this problem, and this problem is done. This is the first example, so maybe it might help if we did one more. So let's do that. Okay, so I have a similar problem. Yeah, I mean, the Squeeze theorem, the first time you see it, it's kind of weird, but it's actually pretty easy to apply. You just have to know to apply it. Okay, this problem is going to be even better. Okay, so once again we want to use the Squeeze theorem to show this. Limit as x approaches 0 of the square root of x cubed plus x squared multiplied by the sine of pi over x Okay. We want to figure out what this limit is. All right. So we're going to use a similar. We're actually going to use basically the same argument that we did last time. Okay. So we want to think about, is any part of this bounded in general? Okay. Well, first of all, let's see. Well, okay. You know what? Let's not make it complicated. Let's not make it complicated. The sine part. We know the sine is bounded. Let's use that. Okay. Sine of pi over x. We know that the maximum that this can be, the sine of pi x is always less than or equal to positive 1. It's a trig function. It's a sinusoid. It's sine or cosine. Sine and cosine are bounded by negative 1 and 1. And likewise, it's going to be greater than or equal to negative 1. Okay? And so, just like before, what this means is that since this is the minimum, think about plugging this in here. That would turn this entire expression into the following: limit as x approaches 0. And now if this is negative 1, then we just get negative square root x cubed plus x squared. Okay? So this has to be less than or equal to the limit as x approaches 0 of the thing that we're trying to figure out. This is the thing we're trying to figure out. And just like before, the sine part can never exceed 1. So this expression is always less than or equal to the limit as x approaches 0. And then just replace the sine part with a 1, and all you get is the square root x cubed plus x squared. Okay, now, just like before, the left, let me change my color. This function is continuous at x equals 0. At least it's continuous from the right hand side. We have that one-sided limit going on. Same thing here, right? So if I just plug in 0 to this expression, I get negative square root of 0 cubed is 0 plus 0, less than or equal to. And I'm gonna leave this alone. I'm not gonna change this at all. Oops, I forgot. Oh, I'm sorry. Let me erase that. On the right here, on the right, this little right blue arrow. Again, it's continuous. So I'm just going to plug in 0 to the square root part here, and I want to get the positive square root of 0 plus 0. And the square root of 0 plus 0 is just 0. So just like before, we're here. Remarkably similar to the last problem, and honestly, really every problem that I've ever worked in my entire life with the squeeze theorem uses this. You almost always have to show that it's going to be 0. So now we have our expression, our function, squeezed between two zeros. It's got to be bigger than or equal to 0, and at the same time it's got to be less than or equal to 0. So the only way both of those can happen, of course, is if the thing in the middle is exactly 0. So just by considering the max and the min, showing that the max and min are 0, If the max and min are 0, then that means the things in the middle have to be 0 as well. And that's the thinking and reasoning behind the squeeze theorem there. And honestly, basically every problem goes a lot like this. So I think I'm going to go ahead and call this one.